Greeting. Thank you so much for giving the opportunity to discuss responsible generative AI at your conference and how this can be adopted within the enterprise. What are some of the promises and what are some of the challenges in this area? We're going to briefly look at some of the evolution of generative AI and then look at some research that Google has done throughout the course of this, and then look at the essentially the adoption and the life cycle. So in terms of background, some of the concepts, generative AI has been distinguished between predictive AI and generative AI, whereas in predictive AI, we have classifications and regressions and forecasting. In clustering in traditional senses, we have historical data, and we'd like to apply it to out-of-distribution data, new data that we see. And it often requires supervised learning, which enforces labeled data in the input-output pairs. And whereas generative AI generally creates a new data set based on patterns that it has realized within the existing underlying, often very large training sets. They could be, typically they started out as text data sets, but have gone to image and other modalities. The training data isn't really very specific to a particular task, whereas in predictive AI, we're very focused on, let's say, if we're doing a regression, that particular task, whereas in generative AI, there are possibly hundreds, if not thousands, of downstream tasks like summarization, entity extraction, sentiment analysis, et cetera, that we typically do with NLP models, and then more broadly with different modalities of these models. So in this sense, we have the notion of pre-training that is commonly used in generative AI to learn the underlying features, often very general features from large data sets, before actually fine-tuning them on specific data sets. The way we employ generative AI is usually through an engineered prompt. And so that prompt is refined over and over again through a trial and error until you get to the output you would like for that specific task, that generative AI task. In contrast, in predictive AI, you're giving input-output labels and of course, splitting them into train, test, and validation sets. But what you're looking for the neural network to find is the function. The actual, that's why they're calling neural networks function approximators in predictive AI. And so with that, what was a very transformative experience in the industry was, pun intended, the introduction of transformers. Back in 2017 by Google Brain and the University of Toronto, collaborations in the Attention is All You Need paper, where the introduction of the notion of multi-headed attention in an encoder-decoder architecture for language translation was initially done. Throughout the years, Google has been building larger language models over time, and other companies have picked up at that point and are progressing along those lines. The generative pre-trained transformers, the GPT models, are very important examples of these. BERT, T5 models, Lambda and PaLM models, which are Google-specific models, have been developed. And Google basically uses these models to back-end a lot of their systems and products. But recently we've announced, in fact, today there's a concurrent announcement with the Data and AI Summit, which talks about new offerings in generative AI. As we look at the path that products have taken and the research behind them, we can see various models that have been used, such as the BERT model, the T5 model, as the backbone for a lot of the other companies and researchers who are employing them to train new models and new variations of these models. Two of them stand out. One is the Pathways language models with 540 billion parameters, which enables us to essentially accomplish thousands of downstream tasks. And then the Lambda model, the language model for dialogue applications, which was published originally in 2020, which was very focused on dialogue versus just the downstream tasks. So it would maintain state, maintain conversational state. And this was the basis in 2023 for the introduction of BARD, which is an application, a consumer-facing application that you can access today. Bard.google.com, it's available to everyone in preview form. And this has the Lambda model behind it. Essentially, it's an application that is powered by Lambda. In 2021, a group of researchers came together at Stanford University and decided to compile about a 200-page document which describes the opportunities and risks of foundation models. And this is really what I'd like to emphasize, that these foundation models have lots of opportunity embedded in them, but there are lots of promise, but there are challenges that we need to face. And this is one of the primary things I'm going to be talking about today. So these foundation models are typically trained on multiple types of modalities, including text and image and speech. And a foundation model is created that should then be adapted before going into the wild for answering these types of tasks: question answering systems, sentiment analysis, etc., object recognition. All of these downstream activities can be conducted on foundation models directly. But we feel, and the researchers in this paper, which is a very large paper, it's more like an encyclopedia, a 200-page book almost, which talks about the pros and cons, the challenges and the promises of foundation models and how we need to adapt them. So with a typical iconic representation is a text image diffusion model that people are very used to these days, where you can essentially type in text and get an image from that text. Or you can essentially look at something like conceptual understanding, where models can distinguish between cause and effect, understand combinations of conceptual elements, and explain jokes, describe what, in this case, using emojis, what movie does it describe? So these are complex conceptual understanding tasks that are done. Another one is the chain of thought prompting, which pertain to this research paper that was published as a blog called Language Models Perform Reasoning via Chain of Thought. So you can think of a chain of thought, and chain of thought prompting is essentially different in that what it produces is the path the language model took to arrive at the answer. And this is super important because the idea is that you can not only utilize these models to understand what goes on. So from an explainability in terms of responsible AI, there's a notion of explainable models that is important. So this lends itself a little bit better to understanding why a model came up with the decision that it did. And therefore, you can parse these into segments of this chain of thought. So concentrating on two of the major models, as I mentioned, the pathways language model is characterized by the fact that the entire neural network, even though it's a densely coupled neural network, you don't need the entire neural network at one time. You can literally, as the name suggests, define a path through the model that actually produces one of these many hundreds and thousands of downstream tasks. And then the next one, the language model for dialogue applications, not only does it generate conversational interaction, but the important other thing it does is it allows you to classify various types of things that it outputs in terms of safety, in terms of sensibility. Is this thing sensible? Is it specific to the query, the conversation that was being made, and how interesting or nuanced or contextually fine-tuned it was to the responses to the actual prompts. So these elements combined produce a plethora of models that a lot of researchers around the world are working with. And one of the things that is highlighted here is that larger and larger models are being built so that they are exhibiting what they term as emergent behavior. And what that emergent behavior is that if you build a very small model and it can do 5 things, let's say, if you build a model that's twice that size, it won't necessarily do 10 things. But if you build a model that's 10 times the size, it may exponentially go. And that growth is characterized by a huge amount of additional things the model can do, patterns it can detect among the different tasks that it can accomplish. And so this has led to the training of larger and larger models. They have overwhelming computational requirements, meaning the cost of training and inference is basically increasing with model size, no surprise, and therefore the need for acquiring higher and higher quality data is paramount. So with this, there came a realization that was published in this paper in March of 2022 by DeepMind about if you have a fixed budget of floating point operations per second, what should the trade-off be between the size of the model and the number of training tokens, the data? How much data should we train the model on versus how big the model should be? Everyone before then thought they should just go ahead and build bigger and bigger models. What this paper is trying to communicate is that you can build a model like Chinchilla that is a fourth as large as this other model called Gopher, which is a conversational model. And yet, if you train it with 4 times the training tokens, you can get comparable, if not better, experiences and outputs from it. So the common, if you will, set of models that are out here characterized by various qualities such as being language and visual, or in the domain of robotics, etc. One of these models I will select just as a representative example, the Sparrow model, which is a relatively smaller model, 70 billion parameters, that's fine-tuned and prompted. So what is interesting about this model and the way these models are trained is that they were designed to improve the alignment of dialogue agents by targeted human judgments. And they were designed to create less toxic, less potentially harmful, less incorrect outputs. And this was done by reinforcement-based human feedback, factual grounding, which means that when it makes a claim, it needs to support that claim with evidence. And essentially, the other very important characteristics that this model has is that it was governed by a set of rules, a set of very deterministic rules. So it wasn't just unleashed in terms of training and in terms of inference, but was trying to comply with a set of very explicit rules, which were trying to avoid any kind of aggression, any kind of threat, harassment, any negativity that we would consider as part of this rule set. So if you look on the left-hand side here, this Sparrow model was trained by a combination of identifying the rule, the degree to which the output was conforming to the rules, the degree to which the output was conforming to the quality of measuring the performance of these models. And then both of these were fed into human feedback through reinforcement learning mechanisms. And then the output of that was fed back into the model in this very constructive feedback loop. So the outcome of this is that you can build safer dialogue agents and improve this alignment between dialogue agents and human feedback. So you're getting better and better, more expected, less toxic kinds of, less hallucinatory, in fact, types of outputs. So in terms of enterprise, so that first part was more of, let's look at the history, where it came from, what the challenges were, what the criteria were for the size of the models, the data, and what characteristics, how these models should actually be trained in different senses. Now, we know there are compelling reasons to improve and expand on these capabilities of these foundation models, and that generative AI has had an indelible mark on everything in all industries in some shape or form, lesser or greater. And for example, even in, of course, in machine learning, in enterprise applications, the consumer domain, and education and research, and the implications are there in terms of sustainability as well. So one important thing to look at is this generative AI lifecycle. and how generative AI changes the life cycle that we have come to know. So as these models are getting larger and larger, and these pre-trained models are coming into the forefront, it is important to note that the data and the data efficiency is one of the key points of reference for conversational AI, where in pre-training you have on the order of billions or trillions of tokens or examples, and in fine-tuning these models for specific domains, you can now get down to tens of thousands of examples. And then when you're doing prompt tuning, you have on the order of tens of examples. And essentially, it is important to realize that you don't necessarily need to fine-tune the model to create a new model. You can actually use the pre-trained model for many applications adequately enough to awaken, so to speak, these quote-unquote superpowers by just appropriate prompting, asking the right questions, giving it a very clear specification of what should be done. So there is a blog that I've written which describes this generative AI lifecycle. If you'd like to look at the blog, here's a QR code that you can take a picture of and check it out. The typical machine learning model we all have come to know is basically to collect and validate data, prepare it in some way, train the model, evaluate it, and once it's validated, deploy it into production and then start monitoring it. And periodically, when that monitoring detects any skew, to basically retrain it using a pipeline and MLOps-based approach. And this is fair for predictive AI. But for generative AI, this experimentation, and in the era of transfer learning, in the era of large language models, where pre-training becomes an important part, in-context learning has mostly been replaced by fine-tuning for large models, it's extremely important for us to understand that for the enterprise adoption of these large language models, we need to add some phases to the life cycle in terms of other types of iterations for model development. This includes a very, very important step of adaptation. And that adaptation phase is trying to address three main things. The AI safety, which has to do with privacy and bias and toxicity and polarization avoidance, as well as managing and mitigating misuse of these models. And then, of course, the robustness of the models themselves. These should be characterized within the model cards, which are the metadata that describe these models, which talk about what the test cases were, the suitability of a model for a task, and how the data was curated. And in fact, another kind of skew, another kind of drift, which we're terming adaptation drift, needs to be taken into consideration. So in the past, we would have data drift and model drift if the distribution of the data changed, if the model started performing worse. But in fact, here, it's super important for us to also look for things that we're just calling adaptation drift. So in terms of safety issues, in terms of misuse issues, and in terms of the robustness of the model itself, these could be elements of drift that occur as the model is being adapted in the enterprise. And so these are factors that need to be monitored. So where does this adaptation come in? The very macro level of these elements pertains to the data pipeline and preparation, training and experimentation. These are all similar to what they used to be. There are certain things that we'll look at in just a second, but basically what we can see is that the adaptation is characterized here in the middle. And let's see what this implies. So there are various repositories at each stage in the life cycle for ML, whether we have lakehouses and feature stores, model hubs that store various models in them, or model gardens, as we term them, and looking for responsible AI in terms of known biases and misuse factors, as well as the model registry, which contains the model card, which contains the metadata about the model. And lastly, and very importantly, the area of prompting, where you have a database of prompts that need to be engineered or reused based on known successful attempts that you've made in the past for these prompt engineering. So with that, briefly describing this notion of what are changes here in the preparation of data, the significant change is that there is a possibility that you have to prepare domain-specific data, select which downstream task you want, and then evaluate for safety in that particular downstream task. Evaluate the data for bias and safety. And then, of course, the idea of selecting the model, which pre-trained model. I have a model garden. Which of the models in that garden, let's look at the model cards and determine which is the best fit for these tasks that we're looking for. Is it a task for, just simplistically, is it a task for summarization versus generation? Is it a task for entity extraction versus, for example, creating some kind of a knowledge graph? So the selection of the training model becomes the pre-trained model becomes extremely important in combining the actual data. Now, on the data preparation side, yes, of course, all the original ML data preparation is all valid, but in addition to that, you may need to have to do programmatic labeling, because once you want to fine-tune your models, or you detect drift in these models of some nature, you will have to curate and label the data again. And this is a very manually intensive task that is well served if you do it programmatically, if you automate the process of labeling the data so that you can then train a model that is more reliable for your domain and your specific business. So these are the types of things that are going to be important from the perspective of the experimentation and the data preparation phases. So these are all characterized by elements that we're talking about here. And then, of course, in order to do the experiments, you have to train your data. And there are various ways in which you can do training, especially since these models tend to be very large. If you are, in fact, training these large models, and not everybody should be training these large models, but should be using them primarily. But you have data parallel, model parallel, and federated learning mechanisms for training. So then comes the adaptation phase, where now you have a model, but before you unleash it in the wild, so to speak, you need to adapt the model. You either need to prompt tune the model or instruction tune the model, which doesn't change the model in terms of creating a new model out of that model, where fine-tuning actually generates a new model based on the old model. And you may have to distill the model, meaning you may have to go and perform certain quantization techniques, which basically compresses the model down to a much smaller size. Or train another model that is a model in a teacher-student kind of paradigm, where the resulting model is essentially much, much smaller than the original model, but is very focused on that downstream activity that you've trained it for. It is learned from the teacher model, but it has very strict capabilities in terms of producing the outputs that you trained it for. But it is much, much smaller so that you can actually deploy it in a very cost-effective fashion, not only in terms of cost, but in terms of latency, because as the larger models get larger, the latency of running through the model and performing inference also impacts the performance of the model. So once these decisions around how to tune the model is made, the distillation of the model for deployment is made, then the adaptation turns its focus to the AI safety, misuse, and robustness discussions. And from there, this kind of summarizes the discussion that I suggested, whether it's transfer learning, fine-tuning of the models, which is basically updating an existing model with new data for a new task, or in transfer learning, where you're adapting a pre-trained model to a new task or domain that it was not originally trained for. And then the safety mitigation of the models to ensure that the model is safe and ethical and trustworthy, partially at least explainable, and how you can mitigate the misuse of that model, as well as improving its robustness. Again, we talked about distillation, and various distillation techniques are outlined here and further in that blog that I cited. But the distillation approach can be done in many ways: pruning, quantization, knowledge distillation, etc. And then I described the teacher-student distillation as well, where you take a larger model and train a much smaller model in that. And then, of course, once you deploy the model, you are obviously validating the model from various angles of performance and capability in terms of safety, which comes with the adaptation. And you deploy the model and start monitoring that model. Now, the prompt engineering side, or the instruction engineering side, so prompt engineering would include prompt design, prompt tuning, and instruction tuning the model, so that you're not essentially changing the model as you would when you fine-tune it, but you change the type of output. You condition, you put in guardrails so it produces something that is more along the lines of the output type you're expecting it to. And so that would require trial and test, and effectively selecting prompts that have been working for yourselves or other people in the enterprise prior to that, and iterating over it until you find the necessary engineered prompt that would work best for you. Again, here we're distinguishing between prompt design, tuning, instruction tuning, and fine tuning. And you can read more about that in that discussion. Here we have a briefer time frame, so I'm not going to go into too much of that. I am going to focus on a few of these safety considerations. One of the things with foundation models is that they could be potentially a single point of failure if they're not adapted correctly. Because of their generality and ubiquity, they are imbued with a strong security and privacy set of properties. And if that is so, then, and they can form the backbone for a design of a secure and reliable ML application, then the time that's put into securing and making sure that model is performing well in a secure fashion, taking into account privacy of what was used to train the model, these all form the corner foundations of avoiding a single point of failure. The other aspect is in data poisoning, where there is some amount of permissiveness in data collection. So if someone could potentially start training the model with some data that someone had injected hateful speech, for example, targeted at a specific individual or company or minority or some group, that could train and condition the model in order to produce outputs that are totally undesirable. And since these models are growing more and more accurate and more powerful, it's important to make sure that that adaptation is occurring at the data side as well, on the data preparation side. So there's governance around how that data is collected, what kind of speech, what kind of data is actually being fed and trained on these models. There could also be not just data poisoning, but function creep. So what is function creep and dual use? So in this particular example, there was a model card of a foundation model called CLIP, which is a visual model. And the idea of the model was you gave it an image and you gave it text, and it would predict something about that image text pair. Now, in trying to do so, the model actually was predisposed to try and learn the internal representation of the images. If these images were human, it would actually try to capture the facial features of those individuals. And this is mentioned in the paper that I'm citing here. The model card, if you look at it, never explicitly mentions, and was oblivious to the creators of the model, the fact that facial recognition and other surveillance technologies were deemed to be out of scope, whereas in fact, CLIP was able to actually understand the facial features, and therefore inadvertently, this was function creep and dual usage. So the fact that CLIP could be repurposed for such tasks was unintended, but the consequence of the model trying to learn certain things was that function creep happened. There's also the notion of a multimodal inconsistency where you have two different modalities that are coming in, let's say vision and text. So let's take an example of an autonomous driving system that primarily relies on vision, and it sees a billboard that says green. It actually has the word green on it. So how should the model interpret that? Should it interpret it as a green signal? Should it go, or should it stop? So these types of things that the model can mistake its actions on are extremely important for us to get straight in the adaptation phase. So these multimodal inconsistencies, this function creep, the data poisoning, and avoiding single point of failure here. I'm going to only talk about one additional thing, which is the AI safety aspect again, where if these models are controlling systems, this is a key challenge in terms of the catastrophic, the control problem initially, and then we'll talk about the catastrophic robustness failure. In the control problem, it's important that the AI we have a throttle, so we can shut off the AI. So we can essentially, if it's deployed in an environment where it controls things, then we are able to control that AI essentially. And a key challenge for AI safety is goal-directed behavior, may be emergent, similar to the function creep, where, for example, if the optimization goal on social media is engagement, then elsewhere it could behave in a different way, meaning it could make inscrutable decisions. And basically, if it's trying to over-optimize on engagement, it may produce content which bring about engagement, but have dire consequences in terms of division and polarity and building fake claims, etc. So it's important to understand that goal-directed behavior can have emergent behavior consequences that are negative. And therefore, the control problem and the catastrophic robustness problem need to be handled as well. So I think I'm out of time right now. So I will conclude and thank everyone for listening today.